So today's agenda, really, an overview of the technology. Feel free to ask questions. It's a fairly interesting thing to work on, so I can go as deep or as wide as you want. And then we want to talk about specific use cases that we have for our technology that we're seeing in our customer base, and maybe expound on why it is that they're choosing ClearSky for these things, specifically application mobility and disaster recovery. And also we have a newfound focus on machine data and analytics, time series analytics that seems to be getting a lot of traction with the ClearSky space. So what are we? ClearSky is a global storage network. We deliver enterprise storage spanning the entire lifecycle of the data as a fully managed service. So what does that really mean? Well, you think of us as a service that delivers all of the economics and scalability of the cloud, but gives you the reliability, the security, and most importantly, the performance, low latency and capability of enterprise storage, all in one pay-as-you-go service. The world today is highly fragmented, especially in data storage. You saw today and yesterday how VMware is talking about this cross-cloud functionality. We're moving into a world where we have silos of data, and this is how we were seeing the world 3 years ago when we were starting the company, and it's turning out to be more and more of a problem when people start to talk about cross-cloud. You have your on-premises stuff. I'm sorry. I gotta say the right word.
Especially in this crowd.
You have private cloud. There are managed cloud providers, some of them maybe even in this room, and the public cloud. And you have silos of data between all of these. So it's very, very hard to do things across these silos. And apps tend to be sort of more or less anchored to the silo that they live in because the data footprint tends to grow very large and unwieldy, and it's very hard to move. ClearSky's vision is that you need a new architecture, something that is more data-focused, data-centric, and allows a single view of all your data regardless of the environment that it's in, and provides the same level of high performance, low latency, security, elasticity, and capability across all the environments, so that you have this really consistent way to manage all your data, regardless of where it physically resides. Obviously, because it physically will reside in multiple places, you need to have a network. A network is a very, very crucial component in any type of a system like this. So when we talk about building a global storage network, we are actually building a private network so that we can move data at very, very high speed across dedicated links, anywhere you actually want to access the data. So accessing your data anywhere it resides, anytime you need it, is something that we've taken to heart and something that we're delivering today. What is it? More specifically, the network is it's a metro-based service. So we run out of points of presence in various metro areas inside of the United States, at least initially. And we do this for a very specific reason. Latency is a problem that we need to be able to solve for certainly any type of remote storage. And so we run out of metro areas. We sell in those metro areas where we exist. We sell primary storage as a service. So it's on demand. It has all the capabilities of primary storage. And with it, we also have capabilities along the lines of disaster recovery and archiving backup functionality. All of that is kind of included in the service. And we wrap it up in a very, very enterprise class SLA. So we built the system out to be 5 nines. We have an SLA that guarantees uptime, and we give you credits for any time that the service is down. So what we're trying to do is change the way enterprises consume data. We want to eliminate the storage silos. We want to give enterprises the elasticity of the cloud. So in other words, pay only for what you use. So only the usable storage and only the stuff that you've actually written to. And you want to have an uptime guarantee, something that is at least comfortable to the set of folks that are running enterprise infrastructure today. And also, you want to get multi-site access without having to take on the cost of data replication. And so this is key to our data recovery story, and it saves a lot of money, time, and pain for customers. So let's talk a little bit about the consumption model, because this is something that I think it bears some relevance given what's going on in the conference this week. In today's world, what you do is you buy storage in buckets, discrete buckets. In this example, we have a 100 gigabyte bucket. So you want 400 gig, you get charged 400 gig. And then you proceed to use it. Even though you're thin provisioned, you're actually already paid for this stuff. So whether or not you think you're using it or you're not, it doesn't matter. You've paid for it. So this is the consumption model that we have today, buying in large discrete buckets. So regardless of what you're actually using, you've already paid for it. With ClearSky, we have true on-demand capability. So not only are we thin provisioned, but we only bill you for the individual bits that you've actually stored in the network. So this obviously can save you a lot of money, and it also lends itself to that very cloudy sort of economic model that we talked about. If you delete data, this is something you can't do today in anybody else's infrastructure. We actually just reduce your cost. So you have that full elasticity going up and down, and your costs are reflected within a month of you deleting data. You can also just bring on data whenever you need it, and it's just simply there. We're backed by a public cloud. So the solution itself is a caching network. We used to call ourselves the Akamai of primary storage way back when, and then.
Can I ask you something about
Sure.
The previous slide? So, do you charge per minute, day, month? I didn't understand. Because it changes a lot.
It's per gig per month. It's per gig per month, and we actually have a formula where we take an average of the capacity used over the course of the 30-day billing period, and then we subtract the extreme. So we remove, like if you had a really big, work day where you had a lot of data but then deleted afterwards, that will get dropped in the sample unless you do that every day.
So if I need just 200 gigabyte more at the end of the month per one day because I'm doing some analytics, I'm actually not paying for everything.
Yeah, we will drop it out of the average. If you're doing it all the time, it's different. When we get into the way the plumbing works, the system is designed for that level of flexibility back and forth. But you will, if you do it every day, if you incur that kind of a thing every day, we will pay attention. You will alter the average, and your average capacity consumed is going to be up there.
But if I do it the second of every month, I'm cool.
Yes.
Is it second, minute, hour, or daily meter?
Daily metering. Okay, moving on.
Hold on.
Yes. So we're a caching solution. We built a system that separates out the hot data, the stuff that is used over the course and accessed over the course of a week. The warm data, which we define as the data that's been touched over the course of some number of months, and that's a variable number, but think order of months. And then cold data. Actually, cold in our definition is a copy of everything, because everything goes into the cloud, and we use the cloud for durability in the system, and I'll get into that in a second. It's a caching network, and the key to remember is that the data that you're actually accessing is accessed out of a cache. The data that you're actually writing is actually written to a write-back cache, and you're never actually interacting with the cloud in any form. So this is one of the ways in which we've solved the latency problem. So the way we've implemented this is through this series of POPs and a very high-speed dedicated network. So I usually start in the middle when I talk about the overall architecture. In the metro area where we set up, we usually pick a building. It's usually Tier 3, Tier 4 data center that is secure and reasonably up to snuff. We set up a small stack of equipment there. We have caching infrastructure, which is object storage that is highly engineered by us to get a certain level of performance, and it's scale out. We have compute resources that are partitioned on a per tenant basis. So we have multi-tenant software-defined storage essentially sitting in that point of presence. And then we have a lot of very, very high endurance flash attached to that compute. And that serves as a write-back cache. And so every tenant gets their own partition of write-back cache. And it's set up in such a way so that the size of the write-back cache could never be overrun. So you're always writing to that write-back. So actually, you can keep going back. There we go. No, there. Thank you. To the left.
Mark takes instruction well.
Back forth. You know, liquor in my bag. And we can just get rid of Mark.
Yeah, so do I.
I can go home. All right.
Hey, look, we need someone to click. I'll say right, please, left, please. Is that get the protocol right? So going to the left of the middle, we run private lines to the customer's location. So we're taking advantage of Metro Ethernet and EPLs in these metro areas. This is sort of a sleeper technology. It's actually commoditized itself quite a bit over the last few years. So it's very easy and straightforward to get very high-speed connectivity to pretty much any data center in a metro if it's a well-connected building for a very nice price. We actually include the cost of that into the service, so the customer never actually has to incur the cost or the trouble of having to project manage all of these things. And in fact, we've done a lot of interesting things to make it easier in certain metros to get that level of connectivity. We provision 2 1 gigabit links to every customer. So full dedicated connectivity. We're not doing this over the internet. There's lots of reasons not to do it over the internet, but especially given the SLA that we want to provide our customers. So private connectivity into the customer's data center. We provide them with an edge appliance. The edge appliance is an all-flash appliance. It's the 2U has up to 24 slots. Today we populate the initial load with 1 terabyte devices. We have 6 of them, so about 6 terabytes of cache for the initial. But you can grow that as all the way up to the 24 slots, and that box actually has theoretically enough capacity to hold up to 32 or so terabytes of flash as a cache. They also scale out. So if you run out of space on one, we can bring you up to 4 of them. This is only intended to be the hot data. So in other words, the data that you would access over the course of a week. So if you think about it and frame it in that way, 30 terabytes is a huge amount of hot data. 120 is just an insane amount of hot data. So we have a pretty interesting scale-out story with respect to sizing that edge so that it actually provides the level of flash performance that we need. The cache is highly available. So although we don't manage for durability, we don't make copies of the cache on flash on the edge, we do keep it alive. So we have dual controllers, dual power supplies. It's a shared storage architecture, so if one of the controllers dies, the other one takes over the entire cache. So you always have availability of the cache. What we're trying to do is maintain performance in case of a mechanical failure or fan tray failure or something along those lines.
And SSD failure results in a partial rewarm?
Yes, that essentially will happen, and the partial rewarm is we actually set it up so that no more than about 1/8 or 1/7 of the cache could ever be affected by a single disk failure. So the rewarm, what we're trying to do is balance the amount of rewarm.
Yeah, it sounds like it's got comparable performance impact to a RAID rebuild.
Exactly.
So,
That's what we were aiming for. At 6 terabytes for a lot of workloads, it's oversized. So losing a disk might even be a non-issue at all because it might be just full of cold data. So it works out well. Because it's a cache and we don't have to keep it durable, there's also minimal incentive for us to micro-size it, because adding a little bit of extra flash there, just in case, actually pays all sorts of dividends. So it's cheap insurance. On the other side, we actually write multiple copies to the cloud. So we are direct connected into Amazon's S3 in all our East Coast POPs and also here in Las Vegas. So it's a multiple 10 gig connection. So we run at least 20 gig of throughput to Amazon. It's low latency. It's, for example, from Boston down to Ashburn, Virginia is about 10 milliseconds with our network. So we have, in case everything were to blow up, we have access to Amazon with very, very low latency. And we have some level of performance that we can extract from it if we need to. In general, though, the system is not designed to operate that way unless there's some sort of failure or degraded state. So how does this all work? Next slide, please. Thank you, sir. The active data set is all the hot data that we just described, which is on the edge. In the POP, we have a copy of that active data in another secondary cache, plus all of the additional data that's been ingested over the course of some number of weeks. Now that's a multi-tenant cache, and it waxes and wanes as the requirements of our customers change. But it is largely pretty much everything you've touched over the course of several months. And then what lives in the cloud? Well, really everything. So it's everything you've ever written. And we keep all of that in the cloud for durability. And everything to the left of these arrows is active data. So this is how we manage durability. We do actually have multiple copies in the network of the active data. And the cloud is 5 or 6 copies, so 11 nines of durability, at least in Amazon. Different clouds have different promises, but they're all order of the same magnitude of durability. So that's how we set up the system. Drilling down a little bit further, one of the interesting aspects of our architecture is the way we manage the caching. So writes coming in into the edge, where we support either iSCSI or Fiber Channel today. Writes coming in get immediately processed and routed to the point of presence. So you're essentially synchronously replicating to the point of presence. We write to a write-back cache in that point of presence and acknowledge immediately. And then every 10 minutes, we process the write-back cache and we push it out to our Metro cache and also the cloud. And alternatively, we also can push it out to a remote POP. And I can talk a little bit about the potential use cases for that in a minute. The idea is that the caches and the cloud are point-in-time consistent every 10 minutes. And the POP is RPO 0. So essentially, you have synchronous to the POP and point-in-time to all of the object storage. And we manage that continuously. The caches are sized, the write-back is sized based on bandwidth calculations, so you can't physically overrun it. We also have some slush in there, so if something were to go wrong or things were to slow down or the cloud were to brown out, we actually have enough buffering in there to hold back enough data so that you just can't overrun it given the amount of bandwidth we have available to you. So what does this mean for application mobility? So one of the interesting sort of side effects of being synchronous to a single point in a network is that in our world, inside of a metro, that metro is logically a single storage array to you. So you can move workloads from one spot to another. Now this was kind of interesting because we thought about this stuff like 2-3 years ago, but now suddenly mobility is in. So the keynote yesterday, I was happy to note that now cross-cloud mobility is an important thing. So hey, we thought of it first. It basically means that you can access data in our world from multiple locations, depending on what your point-in-time requirements are. Moving workloads from data center A to data center B inside of a metro is simply a point and click. It's RPO 0, so you never lose any data. It's possible to build a stretch cluster on top of that infrastructure very easily. So it's not inconceivable, although it hasn't been done yet, where a customer might just do availability across 2 buildings inside of a metro, just built on top of our infrastructure. Each location will need to have its own compute in order to enable access to applications. But this is how the basic system works. We also have some really interesting, this is like a really interesting graphic on, how we think about things. So when we sell to customers, we actually talk to them about their disaster recovery capabilities. So because you can just move individual ones from one location to another, you can do things like load balancing relatively easily. So if you have a dark site that's DR, you can actually just use it to load balance some applications that you want to run there. So you don't have to have a totally cold site that's lying unused. You can actually use those resources. It's relatively easy to do. And also, if there's a complete disaster, you simply can just rewarm the other site from the POP and you just run at RPO 0 in the other location. This is actually a really interesting use case for many customers that have multiple data centers in our metros. So we've successfully sold this a couple times.
So you told me that you have new locations now, and one of these is close to Amazon data centers. Can I have a virtual appliance and do the disaster recovery on
in the cloud.
Amazon, the cloud?
It's good that you asked that. Yeah, that's going to come
Hold that
next.
for 2 slides.
Yeah.
Why do you ask
more
that question?
slides. Yes.
Okay. This one, sorry.
Good timing. Just lead them right into it.
Yeah. Thank you. So we kind of build into it. So as we start building out the network, this 10-minute point in time capability actually allows you to take a cached copy, a point in time copy of all your workloads and move them to different metros. So we have the option, if you want to stage your own physical compute in another city, to have us just replicate a cached copy of your data, that warm tier, in another city, and there you have an option of just setting up another edge. And
this is new.
yeah, this is cross metro. And we've had customers that want to do this because specifically some requirements for DR have they have hair on them. Like, for example, you need to be in a different earthquake zone. You have to be cross country. We have one customer that specifically likes Vegas for DR, and so being able to go across metros in some capacity. Obviously, we can't be synchronous. But being 10 minutes point in time is actually a
So it says point in time.
Yeah. So this is point in time. So basically, we're taking those warm caches that are already synchronized with the cloud, and we're making an extra copy in a different location.
But you can always shut things down and then just move it, and there's your clean move. So if it's shut down cleanly, you get everything.
Yeah, and to some extent, I can follow the sun.
Yes. Yeah. So this is something that we haven't rolled out yet, but it's something that we're selling now, and it's a neat feature.
I like that you haven't rolled it out, but you're saying it.
Well, it's coming soon. It's coming soon.
I definitely blame Mark for that.
Listen,
Details.
we got to make money somehow, Howard.
Yeah,
right? Howard. He says it's soon enough. I can sell it, right?
We recently announced the build outs of these 2 POPs, and so it's not it's not a capability that we're missing. It's actually an actual physical deployment thing.
Okay.
So
what's the POP count now?
we are 4.
Okay.
4, and so we have Boston, New York, Ashburn, Virginia, and Vegas.
Okay.
I thought Miami might be one of them.
Miami.
It's right there on the slide.
It's on the slide. We just picked. We were just picking cities.
Well, actually, he picked that one.
I did. My
He
fault.
picked my
You made that slide in February, didn't you?
My wife wanted to go
affordable.
to Miami. It was, that's where the slide came
Which
from.
set mark
Sorry.
failure?
I want to go to Miami.
Yeah, Miami is Miami would be good.
Yeah.
Good idea, Mark.
Hey, there you go.
Are you
Yeah. So,
are you requesting to be the rep for Miami? We're only in February.
In February, that works,
Yes,
right?
okay.
Now, no, right?
So this is one thing that that we're doing, which is it's interesting for specific DR use cases. To your question, Enrico, we have the cloud mobility use case. So your data is already in the cloud. We have one cloud proximal location today, which is Ashburn. So there is the ability to spin up workloads in this manner inside of EC2. So you can, we're already cross-connected into EC2. This is just part of the design of the network. So we have multi 10 gig connections going in there. We have a VPC. So it's entirely possible to just spin up and provide access to workloads across another customer's VPC. So you set up a VPC to VPC NAT and set up the security policies, and lo and behold, you have access to your data. So this is something that is very relevant to hybrid workloads. And
as I said last night, it's the best solution I've seen for hybrid workloads.
And there's probably a whole separate hour-long discussion on the technology we're using on the Amazonized hybrid L2 cache, which is the edge cache inside of the cloud. It's a derivative of the physical technology, but it's also got some very, very interesting capabilities by itself. So you get a lot of really interesting functionality in there, including the performance that we deliver on-prem. So another use case that I'd like to get into. So we have had a number of customers using us to solve time series analytics storage problems. This is it turns out that this is sort of like the big hairy storage problem of today. So the amount of data is enormous. You always see projections like these from IDC, and the types of data are usually they're all time series, they're log data, they're machine data, they're generated by things, not people necessarily, the amount of traffic that these things generate is actually very, very high. Just putting this stuff in the cloud directly is very, very difficult because of the transactional nature of cloud storage. You have to aggregate things, you have to process them outside of the cloud, and then push them in afterwards. And this is the only feasible economic model that you can use. As you know, Amazon and actually all the cloud providers charge you for every in-out transaction. So every write is going to ring the register, and if you have a lot of small pieces of data, each time you do that one little push, you ring the register for them millions of times. It can equal to quite a bit of money. So what we've identified is an interesting spot for us to solve a problem that's very, very related to storage. In particular, Splunk is the area where we've focused a lot of our efforts. Although we actually have a fair number of people looking at other things as well. Elastic seems to be the other big log analytics platform, and there are a few other open source ones that are shaping up to be interesting alternatives. So generally speaking, if you're not familiar with Splunk, I'm not going to get too far into the weeds with it, but it processes and indexes log data, so time series data that come in off of security logs, machine logs, any type of structured text that can be parsed and then indexed. So this is what they generally are used for. The requirements for Splunk are very rigorous for storage. This indexing process is actually a high performance storage workload. But you have this enormous long tail of data, so the data footprint is huge, and so it fits very nicely with our architecture. So next slide. Some of the interesting sort of details of these Splunk workloads. The typical implementation without ClearSky edge device is usually a whole bunch of flash because you need the performance intensive part of the workload on flash. You have huge amounts of ingest, so you need to be very, very stable on ingest. We already have customers that are in the hundreds of gigabytes and terabytes per day of ingest, and some of this stuff gets retained for like years. So in some of the medical related industries that we've been selling, they want to hold things for 5 or 7 years. So that's a hell of a lot of data to have to store on flash. So you have this sort of multiplier effect in terms of the needed storage space. In fact, this was one of the things that was surprising. You buy Splunk, whatever you spend for Splunk, you spend that much more for storage. And Splunk is not a...
Geez, sounds like VMware.
Per socket.
Yes. So, and the storage is a scaling problem. So it creates a huge management problem if you have a lot of data. It's very easy to fill up an existing installation of SAN equipment with log data and then having to buy more and more of it. It's a very big scaling and management problem, especially since you have to do it efficiently across 2 tiers. So, the typical reference architecture has you connecting your Splunk infrastructure to at least 3 different types of storage. You have 3 different management consoles. You have software to orchestrate movement of data across all of these. You have all sorts of other interesting software and management that you have to pull in. So it tends to be a fairly nightmarish type of solution. If you look at what we're doing, we can truck in a simple edge cache, a single 2U appliance, which is your hot tier. And all of the rest of the capabilities just flow right out of the architecture. And all your data is going to the POP as it cools down. It's sitting in the cloud. So we get a very, very nice management model. All you have is this 2U box and a single console for all of it. We've also introduced a Splunk plugin, which is available for download in the Splunk base. So we're going to continue to integrate and innovate in the integration of this workload into our storage. So this is in essence, what we've done is we've applied the architecture to something that is a very, very rigorous workload in terms of both high ingest and high IOPS requirements. Along with huge amounts of capacity required. And what we've done is we've created a solution that's a single box and a single pane of glass to manage all of that data.